and welcome to this episode of Night Sky News for August 2024 with me, astrophysicist Dr. Becky Smethurst. This is the show where we chat about what you should look out for in the night sky in the next few weeks, and then we chat about what's been happening in space news in the past few weeks. In this episode, we've got to chat about JWST's long-awaited look at the crisis in cosmology, which it turns out it hasn't solved like we thought earlier this year, and chat about this new evidence for water reservoirs under the surface of Mars. So this episode is chock full of science. There's chapter markers down here if you want to skip ahead to any specific news story, plus any scientific research papers I mention are all going to be linked in the video description down below, free to read. So without any further ado, let's kick things off and start by looking up. All right, let's start with the planets because there are 6 visible at the end of August and early September. Mercury down closest to the horizon, then Jupiter and Mars all visible in the morning sky, with Uranus and Neptune close by for those with telescopes or binoculars to try and spot. And then you've got Saturn, which will be visible all night, rising to its highest around about midnight. Saturn will appear yellowish, and if you look roughly to the south, you should be able to spot it, remembering that planets don't twinkle in the same way as stars do, so that's usually how you can figure it out. But if you can't, don't worry, grab a star chart app that you can grab your phone and sort of point it in the right direction and check that that's what you're looking at. As for spotting Jupiter and Mars in the early morning sky, you've once again got a crescent moon, aka my favorite moon phase, a toenail moon, pairing up with them to help guide the way from Monday the 26th to Wednesday the 28th of August. So on the 26th, the moon will be just above both Jupiter and Mars, right next to the Pleiades star cluster, making a great sight for astrophotographers and those, again, with telescopes and binoculars at home. Then by the 27th, the moon will be closest to the very bright Jupiter. Then on the 28th, closest to the reddish, fainter Mars. And if you've got a very clear look at the eastern horizon, I'm talking absolutely nothing in the way, looking over the sea, for example, then you might be able to spot the tiny sliver of a moon next to the very faint Mercury in the glow of sunrise on Sunday, the 1st of September. And if you do manage to spot any of this, whether it's Mercury or Jupiter or Mars, then notice how close this all is to the constellation of Orion. It's now visible in the morning sky. And Orion appearing again in our skies can mean only one thing to a Northern Hemisphere astronomer.
Winter is coming.
Now by Sunday the 8th of September, Saturn will have reached what's known as opposition, when it's in the exact opposite part of the sky from the sun. It's like you've essentially drawn a line between the sun, Earth, and Saturn. So this is why it's visible all night, rising as the sun sets and then setting as the sun rises. It also means that Saturn is perfectly lit by the sun right now, so it's the brightest it ever gets in our skies, which means it's just a really nice thing to look out for as we get into September, drawing ever closer to the equinox of equal night and equal day lengths. It means wherever you are in the world, there's a good amount of nighttime to be able to try and spot this. Then on Wednesday the 18th of September, we once again get treated to another supermoon, where the full moon is the closest it can get to Earth, around about 40,000 kilometers closer to us in its slightly oval-shaped orbit, meaning the full moon will technically be larger and brighter in the sky. However, these differences are very slight. It's around about 30% bigger than a micromoon when it's at its furthest point away from us in its orbit, and about 14% bigger. But because you don't have a normal moon or a micromoon to directly compare it to, like in the graphic I just showed, you can't really pick out the differences in the size and the brightness with just your eyes. If you're seeing the supermoon on that night and you think, whoa, it looks so much bigger and brighter than it does normally, I'm guessing what you're actually seeing is the moon illusion, when the moon is much lower down towards the horizon and you're comparing it to everyday objects like trees and buildings, and it only appears larger when in reality it's actually just the same size as always. It's an illusion. I think the only people who really tend to notice supermoons are people in really dark skies, so very rural areas when the moon is very bright and you can get a really clear, distinct moon shadow. That is, if you're not in the path of the partial lunar eclipse that is also happening on the night of the 18th of September, where the moon will fully pass into the Earth's outer shadow, but only just graze that much darker inner shadow, which can turn the moon orange. So if you're in Western Europe, Western Africa, the east coast of the US and Canada, or anywhere in South America, then you should be able to see this fully. I'll pop a link in the description down below so you can put your location in and work out what you'll be able to see and also at what time. Basically, if you're in the right place, then you should be able to spot that the moon looks slightly darker than normal and that there is also sort of a slight nick taken out of it at the top, which is the Earth's inner shadow that's cast on it. And notice how that shadow is sort of the wrong way round for how sort of like the shadow on the moon usually progresses just as it moves through its phases, which I think is why it's so good fun to spot, right? Because it's just a nice reminder that everything's just whirring away up above our heads up there. Now, if you're struggling to visualize all the movements of the planets and the moon and how it ties into what we can see in the sky, that's totally understandable. It's this big 3D thing that's just whirring away with all these moving parts, and it's hard to visualize in your head. Now, if that's the case, I've got something that I think might help. So before we chat about what's been happening in space news, let me tell you about the sponsor of today's video, Brilliant. Brilliant is where you learn by doing, with thousands of interactive lessons in science, maths, data analysis, programming, and AI. It's a learning platform that's designed to be uniquely effective, with their first principles approach to each new topic that helps you build understanding from the ground up. Each lesson is filled with hands-on problem solving that let you play around with a concept, a method that's been shown to be 6 times more effective than just passive learning like watching videos or lectures. Plus, all the content on Brilliant is crafted by an award-winning team of teachers, researchers, and professionals from places like MIT, Caltech, Duke, Microsoft, Google, and more. I absolutely love their scientific thinking course, which introduces you to key scientific principles and theories from simple machines like gears and pulleys to Einstein's theory of special relativity. It'll help build your natural intuition for science while also gaining this deeper knowledge of scientific principles. Plus, it's perfect for learners of every level because there's no complex maths needed. So to try everything that Brilliant has to offer for free for 30 days, visit brilliant.org/Dr. Becky or click on the link in the description below, and you'll also get 20% off Brilliant's annual premium subscription. So thank you so much again to Brilliant for sponsoring this video and supporting this channel. And now let's come back down to Earth and chat about what's been happening in space news in the past month. Now, the first thing that we have to mention is that NASA astronauts Suni Williams and Butch Wilmore are still stuck aboard the International Space Station. They arrived on a Boeing Starliner on the 6th of June on its first crewed test flight. But during the flight, they reported problems with 5 thrusters and 5 helium leaks during either the launch or the docking of the craft to the space station. So they were originally only supposed to be there for this very first crewed test flight of Boeing Starliner for 8 days, and they have now been there for over 2 months. All the while back on the ground, there's been these ongoing tests and analysis to try and work out if it's actually safe for them to travel back to Earth on board the Starliner. Now, as of the day that I'm filming, which is Thursday, the 15th of August, NASA haven't yet made a call on whether they're going to do that or not, or when the astronauts will even come back, but the decision is expected by the end of August. From what we're hearing, it sounds like Boeing is convinced that Starliner is safe and they'll be able to come home just fine, but NASA are being extra cautious, probably given their history of spaceflight disasters with astronauts in the past. In the meantime, NASA do have a plan B already, and that's that they'll come home on a SpaceX Crew Dragon mission that's launching 4 astronauts to the ISS in September, but won't be returning until February 2025, meaning that those 2 astronauts that went to space for 8 days will instead spend 8 months in space. Now, that does bring additional risks because the spacesuits that were developed for the Boeing Starliner can't be worn in the SpaceX Crew Dragon, which means they'd have to do that return flight spacesuitless, which also comes with all of its risks as well. So NASA decision makers are basically just going to be weighing up the risk of, taking the Boeing Starliner back to Earth or waiting 8 months and coming back in the Crew Dragon, and then also the mental toll that this is going to be having on the astronauts as well. Back on the ground though, and the Vera Rubin Observatory's secondary mirror was installed this month in early August as part of its construction in the Chilean desert. Now, if you've not heard that term before of secondary mirror, let me explain. In a telescope, you have the main primary mirror that collects the light from objects in space, and the bigger the mirror you have, the more light that you can collect, so the fainter the object you can see, and also the bigger mirror you have, the smaller the object that you can resolve on the sky. And Rubin's primary mirror is 8.4 meters wide. Now the secondary mirror's job is to then redirect that light and focus it down to the detector, the camera that's recording what the telescope sees. Now at 3.5 meters in diameter, Rubin's secondary mirror is actually one of the largest convex mirrors that has ever been made. For context, it's larger than the Hubble Space Telescope's primary mirror, which is 2.5 meters across. Now, most telescopes do just have the two mirrors, primary and secondary, but Rubin has 3 mirrors to help focus the light down, and this is what gives it its light collecting power and flexibility that allows it to complete its huge survey of the sky that's planned. If you want to know more about the Rubin Observatory and what its goals are, check out the video I made earlier this month about it. I'll link it in the video description down below. Now, onwards to Mars, because this research paper was released this month from Wright and collaborators using data from NASA's InSight lander to claim that there are water reservoirs deep under the surface of Mars. I was so excited when I saw this research paper, and I feel like the in-joke between me and all my colleagues is like, oh, we were all searching for water on Mars all of these years when we should have been searching for water in Mars. So as a reminder, NASA's InSight lander landed on Mars back in November 2018, equipped with a seismometer to detect Mars quakes. Like earthquakes where the ground shakes, but on Mars. Over its 4 years of operations, InSight detected over 1,300 Mars quakes before the mission ended in December 2022 when the solar panels just became too thickly covered in the Martian dust to provide the lander with any power anymore. But with all those detections, the team managed to figure out the interior structure of Mars, so the depth of its crust, its mantle, and its core. So what Wright and collaborators have now done is modeled the data with a few different parameters, including the liquid water saturation, which is shown by the parameter gamma W there, which you can see in their best fit most likely model has a value of 100%, i.e. it's just water, at least for the rocks in the mid-crust area that they've been studying here, which are around about 11 to 20 kilometers under the Martian surface. So they're claiming that there is a huge reservoir of water deep under the surface of Mars, which is huge if true, because it has so many implications for the history of Mars and the age-old question of where did all the water go? Because we know that Mars has polar ice caps, so solid water at the poles, and then we see all of this geological evidence in Martian rocks for liquid water once flowing on Mars's surface billions of years ago. So where did it all go? One thought is that as Mars slowly lost its atmosphere over billions of years because it got bombarded by high energy particles from the sun that stripped it all away, that the water evaporated and was lost to space. But with the discovery of these huge reservoirs, then that doesn't have to have happened. And then there's the even bigger implications this has for the possibility of life on Mars. Because if you've got water deep underground and you've got heat from the planet's interior, you've got the ingredients there for life. Life might be able to thrive there. Life like what we find here on Earth by warm ocean sea vents kilometers down where it's usually pitch black. You know, if you'd asked me like 2 weeks ago about the potential for life on Mars, I would have said, okay, well, you know, like maybe NASA's Perseverance rover might find evidence of past life on Mars. But this new result from Wright and collaborators makes the possibility of life currently existing on Mars just that little bit more plausible. Because, you know, as Jurassic Park taught us,
life finds a way.
But finally, onto the news we have all been waiting for. JWST's look at the crisis in cosmology, aka the Hubble tension. Now, if you've been following me for a while now, you will be no stranger to this problem. And if you remember, back in April last year, I reported on how one of my colleagues, Wendy Freedman, who leads one of the teams using JWST to look at this problem, had presented some of her team's early results on the conference circuit back in spring. But all we had to go on were her slides and her talk. We didn't have a research paper with all the detail yet. But now we do. After this research paper from the research group appeared online in mid-August. It's still not gone through peer review, it's just a preprint after all, but it's still more detail than we had before. So before I get ahead of myself, I'm going to attempt to do what is hopefully a quick recap of the Hubble tension. If you've heard me say all this before, you can skip ahead to this timestamp. Now, basically, we have a few different ways of measuring the current rate of expansion of the universe, what's known as the Hubble constant. Now, that name is a misnomer. The expansion rate of the universe is not constant. It is changing with time. And there are other projects measuring that I've covered before on this channel. But when we refer to the Hubble constant, we're talking about the rate of expansion that is currently happening now. Now, there are two main ways that we can measure this. Firstly, we measure both the distance to nearby galaxies and then the velocity that they appear to be moving away from us because the universe is expanding. And we plot one against the other, and the slope of this line is the current expansion rate, the Hubble constant, h0. When we do that, we get a value of around about 74 kilometers per second per megaparsec. Now, the other way that we can do this is to just model the entire universe, starting with the earliest light from when the universe was just 380,000 years old, what's known as the cosmic microwave background. And then we come up with a model that contains all the known laws of physics and all the known components of the universe, mix it all together, and you try and get from the cosmic microwave background to the universe that we see today. We then find the best fit model to the universe that we see around us, and from that we can determine many different properties and parameters of the universe, like the current rate of expansion, h0. When we do that, we get a value of around 67 kilometers per second per megaparsec. So a value of 67 on one hand and a value of 73 on the other. But these two methods didn't always disagree. They started out agreeing on their estimated value back when the errors on the measurement were quite large, but as telescopes and analysis techniques got better, the estimated errors reduced, and the values returned by each method started to drift apart until they completely disagreed with each other. Statistically speaking, there's only around a 1 in a million chance that the reason these two methods don't agree with each other is because of a statistical fluke, which got a lot of people concerned for obvious reasons, and there's two main camps emerged to try and explain what is going on. Either there's something wrong with our observations of nearby galaxies, perhaps how we're calculating their distances, or there's something wrong with our best model of the universe. Maybe we're missing a law of physics, or maybe there's a component of the universe that we don't know about yet. Now, along with those two camps, there's also two big research teams that fall into one of those two camps as well. One is led by Adam Rees at Johns Hopkins, who's already shared the Nobel Prize in Physics in 2011 for showing that the universe expansion rate was accelerating with time. And the other is led by Wendy Freedman at the University of Chicago, who heads up the Chicago-Carnegie Hubble program to measure this. Now, both research groups have got time on JWST to once again measure the distances to nearby galaxies and see if they change now we've got better data with JWST compared to what we had with Hubble. Now, we've already heard multiple times from Adam Rees's group that they don't think it's the first option. They don't think there's a problem with the distances to nearby galaxies that we're calculating. And we do this using something known as the cosmic distance ladder. Now, the first step on the ladder is to get distances to stars in our own galaxy, the Milky Way, using something known as parallax. Then the next step is to work out the distance to nearby galaxies, where we can make out individual stars known as standard candles, where we know how bright they should be because we've observed them in our own Milky Way, and we know from parallax how far away they are. So from how bright they appear in other galaxies, we can work out, okay, well, how far away are those galaxies? Now, there's a couple of different standard candles that you can use, the most famous being using Cepheid variables, stars that pulse in proportion to their maximum brightness they could reach. But there's other types of stars that we can do this with as well, those at the tip of the red giant branch or the J region asymptotic giant branch stars, which again have a known brightness in the Milky Way, where we already know their distance from parallax. Now, we can't use these measurements of distances to nearby galaxies to work out the current rate of expansion of the universe because they're too nearby, right? Their movements are affected more by the gravitational pull between them than they are by the expansion of the universe. Instead, you have to go another step up the cosmic distance ladder. We need the distances to even more distant galaxies, which are too far away for us to make out individual stars. They're just too faint to pick out. That is until one of them goes supernova and gets incredibly bright and is also a standard candle. So as long as you have a galaxy that at some point has both, a supernova and a Cepheid, or a supernova and a TRGB, or a supernova and a JWST star in it, then you can use that galaxy to essentially calibrate all these steps along the cosmic distance ladder, and then you can measure the rate of expansion of the universe, which again is the value that doesn't match with the value we get from our best model of the universe. And so this is why a lot of people think that, the problem that's causing the Hubble tension is something to do with our distances to galaxies, because this cosmic distance ladder is just one big house of cards that is ready to come tumbling down. So I think the main idea that everyone has been focused on is that this middle rung of the cosmic distance ladder, using these individual stars to get at distances to galaxies, was affected by what's known as crowding. The Hubble Space Telescope essentially couldn't separate the individual stars out because it didn't have a high enough resolution. So the individual brightnesses of the stars that you measure were affected by the stars nearby. So the brightness wasn't very accurate, and therefore the distance that you got out wasn't accurate either. But with JWST being so much larger than the Hubble Space Telescope, it can resolve smaller things and resolve the individual stars so much better, giving you a better calibration for those distances that's then propagated up that cosmic distance ladder to the next step with the supernova and even more distant galaxies. But this is what Adam Rees's group, known as SHOES, has already looked at with JWST a few times now, with Yuan and collaborators in 2022 claiming that you measure the same brightness for Cepheid variables with JWST as you do with the Hubble Space Telescope in the single galaxy that they'd been observed in at the time, which meant there was no change in the distance you measure, which meant there was no change in the Hubble constant that you were going to get out either. Then in early 2024, we saw this research paper led by Rees using data from 5 galaxies observed by JWST, claiming it definitely wasn't the crowding problem with the Cepheids, and again that the distances to galaxies you find with JWST and the Hubble Space Telescope were the same. Similarly, this paper by Anand and collaborators showing the distances you calculate with the Cepheids and the TRGB stars were the same. And similarly, this paper from Lee and collaborators showing the distances you calculate with the Cepheids and the JAGB stars was the same. Basically, that research group are pretty sure that at least with the data they have so far, that it's not option 1. And instead, they've got evidence that new physics is needed in our model of the universe. So, with all of that background info, what then did the other research group that's looking at this find? This Chicago Carnegie Hubble program that's led by Wendy Freedman. Well, they've now used 10 galaxies that have been observed with JWST, which all have supernova in them, and Cepheids, and TRGB stars, and TAGB stars. And they've recalculated the expansion rate of the universe. And note that they originally intended to do all of this analysis blinded, right? Which is where, you're working with the data that you have, but your analysis program puts in like random noise so that you don't see the exact values, so that you can't be biased by the values that you're getting out. And when Freedman presented these preliminary results in April, it was just after they'd unblinded their results back in March. And back then they claimed an average value of the rate of expansion, the Hubble constant, taken across all 3 of these different standard candles of 69.1 plus or minus 1.3 kilometers per second per megaparsec. A value that was not statistically different enough from our value that we get from our best model of the universe of around about 67 to believe that there even was a Hubble tension. Back in April, they were claiming that the problem had just gone away entirely. But then they found there was actually an issue in one of the steps of the analysis that they'd done in their blinded analysis with the Cepheid variables. A necessary correction had been made to the Cepheids twice in some cases. So they had to recalculate the rate of expansion they found for the Cepheid variables, and then also the average rate of expansion they found overall across the 3 different standard candle methods, and their value for the rate of the expansion, the Hubble constant, went up again. So using the Cepheid variables as that standard candle to calibrate the middle rung of the cosmic distance ladder, they get a value of 72.05 kilometers per second per megaparsec for the rate of expansion. Using TRGB stars instead, they get 69.85 kilometers per second per megaparsec. And using the JWST stars, they get 67.96 kilometers per second per megaparsec, giving an average value of 69.96 plus or minus about 2 kilometers per second per megaparsec, which is smack bang in the middle of those two original conflicting values for the rate of expansion of the universe, which is infuriating to say the least. Although it has to be said that using the JWST stars as standard candles, you actually match the value that we get from our best model of the universe. But using the Cepheids instead, you still have the Hubble tension. Now, I was really interested in why this was, why you got the different answer for like the two different standard candle methods. So I dived into this 60-page research paper, and it seems like Freedman and collaborators are arguing it's because you get different distances to the nearby galaxies depending on which standard candle you use. Like, before you've even done the whole calibration of the supernova and worked out a Hubble constant or anything like that, it's the differences in distances that they think is causing the Hubble tension, referring to it instead as a distance tension. So that means that Freedman and collaborators are arguing the exact opposite to what Rees and collaborators are arguing. They're saying it's much less likely that it's new physics, and instead the issue is with using the Cepheids to get at the distances to nearby galaxies. And what I do like about the Freedman paper is that in their paper they list the advantages and disadvantages of using each of these three standard candle stars to do this. And they reckon it's because the Cepheid variables are much more affected by things like crowding, but also dust that's in the way, and also the amount of heavy elements that a Cepheid variable star has in its atmosphere. So much more affected by those things than the other two methods, either the JWST stars or the TRGB stars. At least that's what their initial data from these 10 galaxies observed by JWST is telling them. But it's not even been 3 days since the Freedman and collaborators paper appeared online, and we've already had some reaction from the SHOES collaboration, the one headed up by Adam Rees, with Dan Skolnick posting on Twitter and Deep Anand posting on Blue Sky with comments on the paper. And they mentioned a few issues, which to be honest, I think will just like wash out in the peer review process, like problems with like the uncertainties they're quoting and stuff like that. Except for Skolnick's major issue, which is that Freedman and collaborators only used 10 galaxies that have supernova and Cepheids that happen to have been observed by JWST, and not the full 42 galaxies that have been observed by the Hubble Space Telescope. Now, Freedman and collaborators argued that they only wanted to use the galaxies that have been observed by JWST so that everything is consistent across the board. That's despite the fact that when you then use it to, calibrate out the supernova, the scatter you then get on the distances and the eventual value you get for the rate of the expansion of the universe has more uncertainty on it. But Skolnick argues you should be able to use the full 42 galaxies with supernova from the Hubble Space Telescope if the distances you get to galaxies using JWST and the Hubble Space Telescope agree, which Freedman and collaborators claim they don't, but as we heard before, the SHOES team think that they do. Plus, 4 days before the Freedman paper came out, the SHOES team put out this research paper led by Lee, showing that the distances you get using TRGB stars observed with JWST match the distances found using Cepheids observed with Hubble, which already there's a lot of conflict there. But then Dan Skolnick on Twitter pointed out that if they only use those 10 galaxies to do that calibration step in the cosmic distance ladder and calibrate the supernova galaxy distances, then they get a lower value for the Hubble constant of around about 70 kilometers per second per megaparsec, which is a similar value to the average value that Freedman and collaborators are claiming overall in their latest paper. So that's interesting, and there's very clearly lots to unpack here. And while the Hubble tension hasn't gone away entirely, like Freedman and collaborators claimed in their talks back in April before they realized there was that slight error in their analysis, we've still got two research groups using similar, if not the same, data and claiming the exact opposite thing from each other. It is a scientific headache if there ever was one. And to be honest, it feels like every time there's a new paper published now, it's like just watching this like endless tennis match, just like back and forth and back and forth. So no, I sadly don't have an answer for you just yet on the Hubble tension. Nobody does, but thankfully there is a plan for how to get one, with more data coming for every single step on that cosmic distance ladder. ESA's Gaia mission, which is making the most detailed 3D map of the Milky Way, will soon release more precise parallax distances to the Cepheids, the TRGB and JAGB stars in our own galaxy, so we'll have a much better idea on how bright they're supposed to be for when we observe them in nearby galaxies, for that second step on the sort of calibration of the cosmic distance ladder. Then the Roman telescope, which is set to launch in May 2027, will have a much larger field of view than Hubble or JWST, which means it will be able to fit the entirety of one of those nearby galaxies in a single observation, unlike what we have to do now with Hubble or JWST, where we have to tile or mosaic it and split a single galaxy up. That's crucial because it means you'll be able to fit all of the Cepheids, JAGB stars, TRGB stars in a single galaxy in one single observation. So if there's any noise or systematic from the telescope affecting one observation, it'll affect all of those stars exactly the same, rather than if something changed between one tiling and the next with Hubble or JWST. Then the Rubin Observatory in Chile, which is coming online next year and starting its survey of the sky every single 3 nights, should help us find more supernova in distant galaxies, which will help reduce the scatter when we plot all of this out and reduce the eventual uncertainty on our value of the rate of expansion that we get. I've made videos recently about both Roman and Rubin if you want to know more about each of these observatories that the astronomy community is very excited about, not least because they might finally be able to help us solve the so-called crisis in cosmology. All right, that's it for Night Sky News for this month. As always, if you spot any space news stories that you want me to explain in a future Night Sky News video, or if you've, snapped any pictures of the night sky this month and you want to share them, then send them my way over on social media because I would always love to see them. But until next time, everybody, happy stargazing. So there's chapter markers down. A crescent moon, aka my favorite, oh, I've not got my toenail moon earrings in. My favorite toenail, usually gets cut into as, did you hear my wrist crack then? Oh. Let me tell you about the sponsor of today's Valiant. I think the dog next door has stopped barking, so I am going to open the window. If that's the case though, I have something that I think might... Stupid dog. This is the best thing about cats. They don't bark. Thursday, the 15th of August. I go to Taylor Swift tomorrow. NASA decision makers, blah, 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 blah. Yes, I had a mass panic then that my microphone wasn't actually recording sound. It's a cruel summer. It's cruel because I'm so hot when I film. Average value overall. Motorbike. It's a tennis match, just back and forth and back and forth. Day in and day out and day in and day out. Stars in one same motorbike. Oh, I hate them so much. Dogs, motorbikes, and Chinook helicopters are currently the very top of my hit list. Your names are in red underlined. I'm going to do that again because there was a motorbike that went past again. Have the ire of my hair flick motorbike. Whoa, stupid motorbike is taking me so many takes now. Yay. Whew, that was my last thing that I had to do before Tay tomorrow. I keep forgetting, I'm not just saying Taylor Swift, I'm also saying Paramore, so the inner emo in me is so happy. Oh, I'm still recording, sorry, I didn't realize I hadn't stopped.